Welcome back, I'm that chemist, and today we have important papers in organic synthesis. But today it's a special topic. We're going to be talking about dithioles, which I believe are a universal scaffold for organic synthesis. Why dithioles? Well, you see, dithioles are quite easy to cleave and replace relative to dithianes. They're also really good for preparing rapid analogs, and if you need to tune the reactivity of the dithiole, all you have to do is change the substituents on the aromatic ring. It's also possible to functionalize dithioles using radical chemistry, nucleophilic chemistry, and electrophilic chemistry. And if you begin to oxidize the dithiole, such as to the bis-sulfone, you can also even get some carbene reactivity, which can be desirable. So if you're going to be using dithioles, it's important to consider what commercial building blocks are available. As you can see, the majority of these are available from the company AK Scientific, but you may be able to find them through some other vendors. If you're just looking to make a few milligrams of something, these are all available in gram quantities. But if you need more than that, you're going to need to prepare it yourself, as the price of these may be prohibitively expensive, because this chemistry is still kind of niche. Now, as I said before, it's quite convenient compared to the Cori dithiane synthesis, where you take 1,3-propane dithiol and react that with an aldehyde or ketone to get the corresponding dithiane. This can be used as a protecting group, but then to unmask the dithiane, oftentimes quite harsh chemistry is needed. Meanwhile, it's possible to use silver oxide to deprotect dithioles, which I'll discuss later in the video. Now, if you want to functionalize the parent heterocycle benzene dithiole, all you have to do is lithiate this with N-butyle, or alternatively you can use LDA. If you're prepping your LDA fresh, it's essentially just an extra ingredient instead of using N-butyle, so you may just want to use N-butyle if you're preparing your LDA yourself. Now, if you take this heterocycle and treat it with sodium periodate, you get the monosulfoxide. If you're wanting to get a stereoselective version of this sulfoxide, there's ways to do this using dioxygenase, as I'll talk about later. Then, if you wanted to get the monosulfone, all you have to do is treat this with aqueous potassium permanganate, and that will selectively oxidize that one sulfur to the corresponding sulfone. But if you leave this too long, potassium permanganate likes to oxidize, so it may start chewing away that other sulfur. Now, if you do want to get the bis-sulfone, all you have to do is take the parent heterocycle, treat it with hydrogen peroxide in acetic acid, and this will eventually completely convert both of them to the bis-sulfone via peracetic acid. Now, the advantage of doing this is it may be a little bit more acidic as you continue to oxidize it further and further. This initially can just be deprotonated using LDA or N-butyle, as I said. However, the sulfoxide can be deprotonated using potassium terbutoxide. But if we get to the bis-sulfone, we can start alkylating using potassium carbonate, which is every chemist's favorite base because it's so mild. As I was saying before, we can do a stereoselective oxidation of the benzene dithiole using whole cells of Pseudomonas putida. If that's pronounced incorrectly, I am sorry for being a putida. It is possible to then take this chiral sulfoxide and then do an aldol type reaction, which would afford a mixture of diastereomers because the stereochemistry of the sulfoxide is set. It's then possible to separate these diastereomers and then selectively reduce the sulfoxide back to the benzene dithiole using this rhenium oxide tris chloride bis-diphenylphosphine complex as a catalyst, with triphenylphosphine as the reducing agent. I don't think that this chemistry is optimized as it's quite old. However, this may still be useful for you if you're trying to get specific stereoselective products. While this is the end of where the authors explored this chemistry, you can see that there's still a CH there, which could then be functionalized further if you wanted to add other R groups in there. So this is quite a useful strategy in my opinion. Another cool thing that you can do is if you take that monosulfone, you can then chlorinate the alpha position using sulfuryl chloride, which is a more convenient version of chlorine. Then, once you have this monochloro product, using potassium hydroxide and 18 crown 6, it's sufficiently acidic at that position to form the corresponding carbene. When they formed this carbene, they didn't observe any of the dimer products that you would get when you form the carbene for the parent heterocycle dithiole, which readily dimerizes and trimerizes. But in this case, it was possible to trap it with this bismethoxy vinyl compound to afford the cyclopropane product shown here. So if you're looking to functionalize an electron-rich vinyl compound, this may be a suitable methodology to do so. Now, why is this a universal scaffold? Earlier I was saying you can add all sorts of nucleophiles, electrophiles, and so on to this. Well, it's possible to lithiate this position with LDA, giving you this lithio species which can then be treated with an electrophile. Alternatively, if you wanted to make a carbocation there, all you have to do is treat it with trityl tetrafluoroborate, and this abstracts a hydride, releasing triphenylmethane as a byproduct. This reaction works quite well, and I've tried it myself many times. While it hasn't been precedented yet, this CH is a very weak CH, and this would be very well suited for photoredox chemistry. So if you're interested in getting a really easy Jax or Angevanta paper, this is one just waiting to happen, because once this is functionalized, you can convert this into essentially anything you want. In addition, if you wanted to do double alkylation, you could lithiate this once, add in an electrophile such as bromomethane or iodomethane. This would add a methyl group here. And then if you lithiate it a second time, you can then add in a second electrophile, and then you have your typical Corey dithiane type synthesis. If you wanted to do aldol chemistry, you could do this with a chiral sulfoxide as well, such as in the Pseudomonas putida stuff that I discussed earlier. Otherwise, you could just treat a chiral lithiated species with an aldehyde or ketone and then get a mixture of enantiomers, if you don't need to worry about stereochemistry. What else can you do with this compound? Well, with the cation, you can treat it with trimethylphosphite in the presence of sodium iodide, doing an Arbuzov-like reaction, which will then give you this phosphonate. This phosphonate can then be lithiated, and you can undergo Wittig-like reactions, except instead of calling them a Wittig, we call it a Horner-Wadsworth-Emmons reaction, to prepare alkenes from this corresponding phosphonate. This can be used to create all sorts of alkenes which still have the sulfurs there, which we call dithiofulvalines, and materials scientists often use this as a way to prepare tetrathiofulvalines as well. Once you take this cation, it's possible to react it with an alcohol in the presence of pyridine and dichloromethane, although some other pyridine-containing bases such as 2,6-lutidine and 2,4,6-trimethylbenzene have also been reported. If you use triethylamine, this will just deprotonate the CH, form the carbene, and this will then immediately dimerize with an unreacted carbocation. So do not use triethylamine or any basis stronger than pyridine for this. You will regret it. The yield of this chemistry really depends on the nature of the alcohol, and it tends to first react with primary alcohols over secondary alcohols, at least when this was used as an obscure protecting agent in the past. If you do need to deprotect this, you can just treat it with TFA and it'll pop right back off. Now, if you take this carbocation and treat it with dimethylaniline, it will react in the para position, giving you this para-dithiol substituted aniline. However, in my own experience, when you use 4,5-dimethoxy BDT, instead of getting the expected benzene derivative, you end up having this quinone iminium type species. This is likely due to the electron donating nature of the two methoxy groups. This isn't reported, but I wanted to share it with you nonetheless, since we didn't publish it. Now, let's say you want to take this bis-sulfone and you want to add in a fluoromethyl group. Well, if you just use sodium hydroxide in THF and acetonitrile, you treat this with select fluor with a catalytic amount of tetrabutylammonium bromide, you'll end up popping a fluorine on there, and this actually enhances the nucleophilicity of this compound quite a bit. That being said, they're both extremely good nucleophiles, both of the green ones shown here, but we do see an 1,000 times increase in nucleophilicity by the addition of that single fluorine. So that's a pretty good enhancement. Now, what can you do with this fluorine-containing compound? Well, if you treat an aldehyde with DABCO, you can end up favoring 1,2 addition and getting aldol-like products once again. If you do this on a Michael acceptor with an alpha-beta unsaturated, such as a substituted acrolein, you'll usually get 1,2 addition. However, if instead of DABCO you use pyrrolidine, you'll form an iminium species, and this then makes it possible to do a 1,4 addition, and if you add a sufficient amount of this starting material, you'll do a 1,4 and a 1,2 addition, which may or may not be desirable. So overall, what you do is you take this fluorine-containing bis-sulfone, this then gets substituted through aldol chemistry or whatever other chemistry you want to do, and then it's possible to reduce off the bis-sulfone using samarium iodide, which can be a little bit air-sensitive, and it can be a tricky compound to work with unless you're experienced using it. You might be thinking, samarium iodide is so expensive from the typical vendor that we buy it from, but if you just look at the price of samarium metal, it's actually pretty cheap. So if you just make your samarium iodide yourself, you'll be saving a lot of money and you won't be paying the vendor tax. So some other cool stuff you can do with benzene dithiole. Well, when you take benzene dithiolyllium, whether it's the perchlorate, which you don't want to use because perchlorates with an organic salt, we have a fuel and an oxidizer, kaboom, maybe don't use perchlorates. It would be better to use like a triflate or a tetrafluoroborate version. If this is used with this nucleoside derivative, the NH2 group of the pyrimidine ring is substituted, giving the NR product. If this is treated with tributyl tin hydride, it's possible to fully reduce it to the methyl group, although it's probably also possible to use Raney nickel or samarium iodide to accomplish the same thing. If you add a Grignard reagent to this benzene dithiolyllium, you'll get the substituted product, which just kind of looks like if you took benzaldehyde and reacted that with 1,2-benzene dithiol using a Lewis acid. However, if you then abstract that hydride a second time using a trityl cation, such as trityl tetrafluoroborate or trityl perchlorate, but again, explosive, so maybe don't use perchlorate, you'll then get the cation once again. If there's alpha protons, they'll be made very acidic. However, since this is a benzene derivative, there's no alpha CHs which could be made more acidic, which means we can add in another nucleophile. In this case, the authors added in methyl magnesium bromide, which then gave the methyl substituted product. And to oxidize this off, they first used chloroamine T to oxidize the sulfur, and then used mercury chloride to accomplish the cleavage. Now you might be wondering about tributyl tin hydride on the ether derivatives. Well, when you use tributyl tin hydride, instead of fully reducing it off, it only adds a single hydrogen on there. So if you wanted to selectively reduce it without fully reducing the whole thing off, you could use tributyl tin hydride. Whereas for the amine derivatives, it actually fully reduces it to the methyl group. Now, another cool thing that you can do is you can take this sulfoxide and treat it with potassium terbutoxide, and if you have a nitroarene, it will either add to the 4 position or to the 2 position. If you have the 2 and the 4 position both unsubstituted, you'll get a mixture of products, but you end up eliminating water as a byproduct. So overall, this is an interesting way to aerolate dithioles without having to use a Grignard reagent, just using the electronics of the nitro group to enable new modes of reactivity. If you wanted to do cyclization reactions, once you have one of these dithiopulvalines, such as one made using the Horner-Wadsworth-Emin reaction with the phosphonate, you can do so. So this imine, for instance, reacts with this dithiopulvaline in the presence of scandium triflate to afford this cyclized product. It's then possible to reduce this off using Raney nickel-like chemistry. Here they just used finely divided nickel powder prepared from nickel chloride and sodium borohydride to fully reduce it to this tetrahydroquinoline. Alternatively, if you wanted to oxidize it off, you can use mercury oxide with fluoroboric acid, but I would prefer to opt for silver oxide, as mercury salts are typically undesirable to work with, at least for me. When they did this in ethanol, they didn't just get cleavage of the dithiol, they also got oxidation of the alpha-beta unsaturated position, giving this quinolone species. But when they did this in ethanol and ethyl acetate, they didn't see that additional oxidation occurring. Now, another way to prepare dithiopulvalines is using dimethyl acetals with an alpha chloro. So this could be, for instance, made through an alpha chlorination of an aldehyde using N-chlorosuccinimide, and then if you form the methyl acetal using PTSA and methanol, you'd be afforded with a product like this. Then, if you treat 1,2-benzene dithiol with BF3, you'll end up cyclizing, displacing the methoxy groups, and through subsequent elimination, you'll be afforded with a dithiopulvaline. So this would be another way to make these if you're having trouble with Horner-Wadsworth-Emin's reactions for whatever reason. Some other cool stuff you can do. So this is an example of a Horner-Wadsworth-Emin's where they've lithiated this either with LDA and Bewley or DBU with lithium chloride, which is a nice modification. Once this dithiopulvaline is prepared, all you have to do is treat it with an acid, a strong acid, probably something like TFA. This will then make the carbocation, and it can do an intramolecular Friedel-Crafts alkylation. They can then deprotect it to get the corresponding ketone. Alternatively, if you wanted to reduce it off, you can use Raney nickel. It has to be the activated form, but the activated form of Raney nickel is commercially available, as I talked about in the last video we posted, giving this tetrahydronaphthalene derivative shown here. You can also do interesting multi-step cyclization. So here, again, they do a Horner-Wadsworth-Emmons to make this dithiopulvaline, and then treating this with acid, they have a domino reaction where this tricyclic species is formed, and then subsequently deprotected using mercury. But again, I would use silver. Now what else can you do? Well, if you were to take this ketone, do a Horner-Wadsworth-Emmons, and then treat it with acid to unmask this TMS enol ether, you'll have the ketone while still retaining this dithiole. Once you take this dithiole species, if you do a mercury deprotection, you'll get the bis ketone 29. However, if you use Raney nickel, you'll get the monoketone 28. If instead you were to make a vinyl xanthate and then treat it with tributyl tin hydride, you can fully reduce off that ketone without even touching the dithiole. So that shows that tributyl tin hydride reactivity that we showed earlier really relies on the electron richness of that dithiole, as in this case, it didn't even touch the dithiole. Alternatively, if you wanted to make the alpha-beta unsaturated ketone, you can make the enol ether and then treat it with DDQ to afford the alpha-beta unsaturated ketone 27. So this is a pretty useful handle in my opinion. Another cool thing you can do with dithioles, such as this one that I've shown here, is you can take it, treat it with an acid, and get some Friedel-Crafts-like reactivity, but the heteroarenes have to be relatively rich. One cool thing that I discovered during my PhD work, though, is if you switch out the acetic acid to hexafluoroisopropanol, usually you still need some DCM to help with solubility, but this reaction will still happen with neat hexafluoroisopropanol. Instead of adding at the 2 position of the indole, you'll instead react at the nitrogen. So with this one reagent, we have 2 modes of reactivity, which can once again be really useful for preparing analogs, especially if you're doing library syntheses. Some exceptions to this, however, are if you have a directing group in the R position, such as like if you had melatonin, instead of getting addition to the nitrogen, you'll always get addition to the 2 position, regardless of if you use acetic acid or hexafluoroisopropanol. Additionally, I experienced when using 3 aryl indoles, you would always get addition to the 2 position. So maybe that's desirable for you, maybe it's not, but overall having 2 modes of reactivity with one reagent is quite awesome. Here's some examples of compounds that we prepared using this methodology. You can also see that if you take the dithiol intermediates shown here, you can lithiate them and add in an R group before doing the fluorination. But basically, if you use silver fluoride instead of silver oxide, you'll get the CF2 compound instead of an aldehyde. Now, the one important thing to note is not all CF2H groups are always stable. If it's a very electron-rich CF2H group, it can readily hydrolyze to the aldehyde. Some examples of that would be shown here. So you can see here's a whole bunch of derivatives that I prepared on some other scaffolds. For whatever reason, when there's a free purity in nitrogen, the fluorination just never seemed to work, but you can still add on the DMBDT group onto these NHs. In the case of electron-rich heterocycles like this methylfuran derivative, instead of getting the difluoromethyl compound, you would instead observe the formation of the aldehyde, just because there's too much electron density, which causes that CF2H to hydrolyze. If you're looking to functionalize these heterocycles, however, you could still do so if you wanted to do methylation, further substitution, as this is a universal approach using dithioles. These are some heterocycles which weren't sufficiently electron-rich to do Friedel-Crafts-like reactivity, although if you were to start doing metallophotoredox chemistry on dithioles, you would be able to couple this to whatever you want. Another thing that we explored with this DMBDT tetrafluoroborate is that you could functionalize alcohols and then get difluoromethyl ethers. This is similar to work that we did earlier with thionoesters. However, instead of having a thiocarbonyl, we could use a dithiole as a surrogate. This worked on amino acid derivatives as well as some more complex compounds, demonstrating that difluoromethylation of alcohols could be accomplished using silver fluoride. We also demonstrated that radiofluorination could be done in a carrier-added manner. Carrier-added radiofluorination just means that 19F silver fluoride is used as the predominant source of silver fluoride, along with some 18F radio-labeled silver fluoride added into it. And then you compare the relative 18F abundance in the product compared to whatever unreacted 18F you had to begin with. So if you wanted to do carrier-added radio labeling with this, it's also possible to use this methodology for that. To prepare benzene dithiolyllium tetrafluoroborate, or even substituted derivatives, all you have to do is take an anthranilic acid, treat it with carbon disulfide, isopentanol, isopentyl nitrite, in dichloroethane and 1,4-dioxane and reflux it. For this reaction to occur, the anthranilic acid is dissolved in hot 1,4-dioxane, and that's added dropwise to the solution of the remaining ingredients. This is done over a period of a couple hours, and I'll include a video of this that I have here. This is a huge scale reaction, and in the case of the dimethoxyanthranilic acid, quite a poor yield was obtained. However, when the metachloroanthranilic acid was used, quite a high yield was obtained. So the yield of this transformation really seems to depend on the electronics of the ring, and if you're able to get a higher yield than this, I would applaud you, because I did this reaction tons of times and I was never able to optimize it beyond like a 20 to 25% yield. Now, at the end of step 1, you'll actually get this isoamyl compound. Here, this OR group would be an isoamyl compound, isopentyl. And in the second step, by adding in BF3 etherate, this starts to react with some of the water byproduct that was generated, which dries it out and generates HBF4 in situ. And you could either imagine that this alkoxy group gets protonated by the HBF4, or alternatively, the BF3 pulls off the OR group, does some fluoride exchanges, and ultimately you get this tetrafluoroborate salt. So if you do this in a one-pot process over 2 steps, it simplifies the workup quite a bit, but if you try and isolate the isopentyl ether, you can, but you'll have to do a lot of washes and it will generate a whole lot of waste. So this is the easiest way that I've found, and I've done this lots of times. Here's a nice pretty pile of the product. Does that make you uncomfortable? It should. But everybody else was doing it in their graphics, so I figured so would I. Now, the reason that we use this dimethoxy is when we were exploring the kinetics of fluorination for this, because we were looking at methodology suitable for radiofluorination, we wanted to have a really rapid desulfurative fluorination strategy. If you were to leave the unsubstituted dithiole or the chloro or the nitro, it will fluorinate fully. It'll just take a few hours longer. It'll even work on this dithiole, which isn't even a benzodithiole, but it is a benzyl dithiole. So all of this is to say, dithioles in general are useful for all of the strategies that have been mentioned so far. It just so happens that the unsubstituted benzene derivative is the most precedented, and the dimethoxy is more rapid if you're looking for more rapid desulfurative fluorination. So if you're experiencing side reactions, you can always play around with the electronics of the ring, and that could be desirable for whatever your suited application is. An alternative way to make this, if you didn't want to use the anthranilic acid route because it's generating CO2 and nitrogen and kaboom, you can instead use disulfur dichloride and get this tetrathiacin derivative. This thing is like brick dust, and it will make glassware really dirty, and this is like the worst reaction I've ever had to clean up after in my entire career as a chemist. So, chemists beware. Despite that, this is probably a more scalable way to make this, as trityl tetrafluoroborate can be prepared via a Friedel-Crafts reaction of carbon tetrachloride and benzene, and then just treated with HBF4 to get the corresponding tetrafluoroborate salt. So this might be more desirable even though it's over several steps, if you're trying to make a whole lot of this. The tetrathiacin can be reduced to the corresponding thiolate using a potassium metal melt, which is then refluxed in 1,4-dioxane with a little bit of isopropanol overnight. This is then added to a solution of dichloromethane in DMSO, which is once again refluxed under nitrogen overnight. This will then afford you with the dithiole shown here, which can then have one of its hydrides abstracted with trityl tetrafluoroborate to then once again generate the dithiolilium. If you wanted to generate that non-benzodithiole, which is a benzyl dithiole, all you have to do is take this phenaceal bromide, treat it with the dithiocarbamate derivative of piperidine. For whatever reason, they use piperidine, and piperidine seems to be better than pyrrolidine for this type of chemistry. You're then afforded with this dithiocarbamate derivative here. All you have to do is treat it with a strong acid like triflic acid. This then converts to the corresponding dithiol, which is still an aminium. This aminium can be reduced using sodium borohydride to afford the corresponding aminodithiol. The aminodithiol can then be deprotected using triflic acid to afford the corresponding dithiolilium. This is a really fun strategy overall. I didn't pioneer this, but I did use triflic acid while previously I think perchloric acid was used. It's an interesting strategy, and this might be an easier way to get some dithiol for you to play with if you don't have access to the other routes that we discussed before. So if you're going to make substituted derivatives of dithiols, you can lithiate that position and then alkylate. So for instance, iodomethane. Once we have this methyl dithiol, it's possible to abstract the hydride once again using trityl tetrafluoroborate, giving this cation shown here. This is a salt that can be isolated. However, it's important to know that this CH3 is highly acidic, slightly less acidic than TFA. Any other acids that I explored besides TFA would show in a 1H NMR spectrum that we actually have this dithiopulvoline. But if you add TFA in, you'll only see a single methyl group instead of these two CHs from the vinyl dithiopulvoline. It's worth noting that the dithiopulvoline has similar nucleophilicity to an enolate, so you can readily do aldol-type condensations. However, it will usually eliminate the hydroxy group. So there's some useful chemistry to be done with these as well, but depending on what you're wanting to do, it's worth knowing that TFA will keep these in their carbocation form. Meanwhile, they will readily be deprotonated to form the corresponding dithiopulvoline. So before I was mentioning that trityl tetrafluoroborate can be prepared relatively easily. This is a process from George Olah, where starting with trityl chloride, you can treat this with HBF4 etherate in benzene, and this will give you the corresponding tetrafluoroborate salt, hydrochloric acid gas, which boils out like crazy, and you have to be prepared for that because it makes a lot of HCl gas, and that is a hazard. And this also generates the diethyl ether, which was previously complex to the HBF4. If you wanted to make other salts, you can instead use HPF6 or HSBF6, but in all likelihood, you're going to want to make the HBF4 salt. So these are the references here if you wanted to check out how to do this. It's pretty easy to make this, so you don't need to go buy it from a vendor. You can just take trityl chloride and do this. It's really easy to do. There's a couple other reactions I wanted to note here at the end. If you take the dithiol, you can use dichloromethane, but it may be more advantageous to use dibromomethane. It's also possible to go from this isoamyl compound directly to the dithiol using dibol, but you might prefer to use sodium borohydride on the dithiolilium, whatever you like, honestly. If you take the bis-sulfoxide, you can really easily take dihalides and then prepare cyclic compounds through an intramolecular secondary reaction. This could then be cleaved off using, for instance, samarium iodide, Raney nickel, and then you'd be afforded with the corresponding cycloalkane. While mercury oxide with HBF4 can be used for unmasking carbonyls, as I mentioned before, silver oxide also works. We never published this, but just like you can use silver fluoride, you can use silver oxide. You could probably even add in other stuff using other silver salts. There's no reason why you couldn't, as long as the intermediate compound is relatively stable. So if you do this with a carbon-containing analog, you'll get the corresponding aldehyde. If you do this with a nitrogen-containing compound, you'll get the corresponding formamide, and if you do this with the ether analog, you'll get the corresponding formate. This doesn't have to be the dimethoxy analog, but it will be faster if you use the dimethoxy analog. I highly encourage you to use fresh wet silver oxide, as the dry silver oxide has poor reactivity for organic chemistry in general. You can also use silver fluoride to unmask the CF2H group. The only caveat is that if you do this on a benzene substituted derivative, it may hydrolyze to the corresponding aldehyde if it's too electron rich, as I mentioned earlier. We didn't explore the full scope of different R groups, so this may not work if you don't have some relatively electron donating R group. But if you do this on nitrogen derivatives, you'll get the CF2. If it's too electron rich, it'll hydrolyze to the formamide, as you would expect. And if you do this on ethers, you'll get the corresponding OCF2H derivative, as I mentioned before. If you wanted to instead get the corresponding methyl group, you could treat this with Raney nickel, and this will work for making methylamines, methyl ethers, and you'll also get veratrol as a byproduct, which is also known as methyl glycol. So just make sure that you're TLCing against this, as you'll be forming another spot that will show up by TLC, which is not your product. You wouldn't just get methyl groups if you do this if you were to first lithiate and functionalize further. So don't just think about this as a methylation strategy. This can be used for a functionalization strategy, broadly speaking. Here's an example where we first lithiated this dithiol and treated it with iodomethane, then subsequently treated it with silver fluoride to get this difluoroethyl group. So likewise, instead of making ethyl groups or ketones, you could also make difluoroethyl groups or difluoro whatever groups, depending on what alkylating agent you add in here. So this is a strategy that might be useful for you. And I really do think that dithiols are a universal approach to making almost any scaffold you want. Now, tetrathiopulvolines and dithiopulvolines have been prepared many, many times, and there's even been 10,000 plus research papers on them. not specifically for organic synthesis broadly, but for material science. However, there isn't a single product that has dithia or tetrathiafulvalines in them yet. If I'm wrong about this, correct me down below, but I don't believe I am. It's likely that over $1 billion has been spent in the past 55 years on these compounds, with no products to show for it. So, the question is, should dithiole research be funded? To all the material scientists working on dithioles, I have a challenge for you. Make one actual consumer product by the end of 2030. None of this, oh, we're currently doing research and there's products, it's in development. That's what all of us say as scientists, okay? That's what we say about every project we're working on. So 55 years of research begs for yet a single product with dithioles in them. So if your research matters, prove it. Prove it. It's been long enough. If you give me $1 billion in 55 years and I can't produce a single product, what should you think about that? Now, to the synthetic chemists, I have a challenge for you. Outcompete the material scientists. I know we can do better. So by the end of 2030, I expect at least one natural product total synthesis to be completed using a dithiole. Additionally, I expect that at least one pharmaceutical can be prepared using dithiole chemistry, at least to prepare enough material to then do biological assays to quickly prepare compounds which could be tested. And finally, I would like to see at least 10 dithiole building blocks at a cost of $5 or less per gram by the year 2030, which is not unreasonable, especially if you're using the alpha-bromo strategy to make dithioles. So I hope that this has been a useful video, and I hope that I've convinced you that dithioles are a really useful approach for making almost any molecule you want. Do you have bigger synthetic problems? Would you benefit from having the eyes of a synthetic chemist looking at your problem? Maybe you're working with a synthesis on demand company who's running into roadblocks, or maybe you're trying to set up your own synthesis in-house. If you're looking for a consultant, I'm currently accepting a few more clients this year. You can send me an email at the address shown below if you want to inquire more. Alternatively, you can also reach out to me on LinkedIn. Thanks for watching, and I hope you have a great day.